Thanks for having me back to the stage. Today we're going to talk about going faster with additive and really two methodologies that we can utilize to do that. Yesterday, one of the ones that we talked about early and really quickly was adding lasers to the machine. Today we'll mention perhaps some parameter optimization that could be done with respect to pre-existing machine architectures, ones that have been in the field for a while, and we can update how those are functioning. You saw that yesterday, so we don't need to look again. Okay, when we take a look at the production of an additive component, one of the things that we need to do is make sure that it makes sense to print the part, and that has a lot to do with business case. I put together this hypothetical pie chart that you can see that takes into account all of the sources of cost that go into what a component will end up, in price point, end up being spent to be installed in a final application. What we can do as a machine OEM is help to shrink that machine portion of the pie slice, and how we do that is make our machine go faster, as fast as possible, achieving the right quality. There are portions of the pie slice that GE can't control and other machine OEMs can't control, and that's the things like how individual businesses are understanding the depreciation of that machine, and for instance, what the cost of some consumables might be, like gas or local electricity. What we can control is how many parts you can get off that machine in a given period of time. If I go from 10 parts per week to 50 parts per week, and that 1 week the machine was 5 times more productive, so those parts are necessarily going to go down in their cost. How can we print faster and achieve the minimizing of that machine impact? So I have on the left-hand side kind of a schematic of one of the styles of laser powder bed fusion machine you might see. And one of the things we can do is recoat the optimize the recoating, excuse me. So a recoat step in laser powder bed fusion consists of a collection. So I need to grab new powder, I need to dose it across the powder bed, and then need to come back and actually return the recoater from where it came so they can begin again in the very next layer. So all of these things take time, and how we can start to think about optimizing is minimizing that amount of time. So we took a really concerted effort on those speeds, how fast it's moving over the collection station, how fast it's moving over the kind of area where the lasing takes place, and then how fast it returns. And so a recent level of effort was put in to really push those to their limits. So I have an instance on the right-hand side where we had a productive Ti-6 4-parameter set and a productive nickel alloy 718 parameter set, where we increased by 100% the collect and dose, and by 300% the return speeds. Now you'll see the asterisk on there, and it says at the very bottom, that's a build agnostic speed. It doesn't matter what I'm printing, the shape of the thing that's going into the box, it doesn't matter. The part is, the speeds are agnostic to what that part is. You'll see that the total improvement column, though, doesn't match up with those 100, 300%. And that's because what's not considered in this effort is what the laser is actually doing. This is just recoating speed. So that one comes with a different asterisk. It's a dagger, I think that's called, for build-specific improvements. So we have one build that we're using to judge the health of these improvements. So despite the fact that we've gone up to 300% faster in certain parts of this build, I'm still getting something like a 32 or 54% improvement. I'm not going 4 times as fast as I once was. Certain parts, yes. The whole process can't be done just through recoater optimization. As an illustrative component, I have up here now a combustor liner made on GE's M2 Series 5, so the same machine that was installed at Pitt beginning of this week. This build is roughly 200 millimeters tall. At the end of the day, it weighs 3.4 kilograms, and this part by itself takes 21 hours and 33 minutes to print. This was done with our new productivity parameter, which uses a 50 micron layer size. At the same time, in a machine right next to it, we started a print with the old parameter set, but making exactly the same component. So in 21 hours and 33 minutes, we got 133.9, so we call it 134 millimeters, and only 2.5 kilograms of that part was manufactured. So really just end-to-end, side-to-side, you can see just through recoater optimization the types of benefits that you could see by pushing on how quickly that recoater is moving back and forth. Because recall, the recoder is enabling the process, but it isn't the measure of success of the process. That's what the laser is doing. So if we can take everything out of that, call it non-particularly critical step, it can end up in a space where the parts are more cost effective because of the time that it takes to build them. So when we saw this single component all by itself was a 31% improvement on how fast we built. Now, it doesn't correlate exactly to a 31% reduction in part cost, but every percent of build time back is going to be a build time benefit that you can take on the cost model for these components. On the left-hand side of this is an eye chart. I'm not expecting anybody to read this, but what I want to kind of show is that most of our materials have gone through this parameter optimization. And what's important to know here is there's no hardware change at all. When you're thinking about requalification of a part or a component to go to these faster styles, the only thing I'm changing is the actual piece of steel that holds the recoder in place. The reason that needs to change is that when we're moving so much faster, the actual process gas that's keeping the chamber inert needs to be able to be fed through the recoder blade holder. There's no software change. There's no major hardware changes. This is purely a new material parameter set to apply to individual components. Okay. The other way that we need to understand about going faster is something that we mentioned yesterday in machine development acceleration. So if you look at kind of the announcements that come out of all of the major OEMs, there's a new model of machine being announced once a quarter if you kind of put everything together. Now, as users of that equipment, you have every right to say, how can I possibly keep up with this? There's no realistic way that I could be continually updating my machine with the same pace that we're updating our smartphones. You would not want to do that just because of lockdown production and comfort level and expense. So the question is, as you look at portfolios of your OEM equipment, and this happens to be ours, how do we possibly move from the first generation of a machine to a second generation of machine without just some enormous amount of expense put into that level of swap? You may be able to justify those things with productivity increases or resolution or part size and say, I can't possibly make can't make a profit on what I'm working on if I can't print bigger. I need an M line. I need a Spectra H. Those types of things are certainly a viable avenue to explore and say the business case makes more sense and I need to change, and therefore the cost that goes along with it is worth it. But on the other hand, if there's no benefit to the business case, why would I change? Possibly, if you want to change, there are methods to go investigate, and I'd like to kind of show you the statistics of how you might go about making that swap, whether or not a business case is driving that activity. So how you do this is start with a baseline. In the last few days, we've heard time and time again that there isn't a material data package that exists for general design, and I agree. There isn't an industrial available data set that you can use to design components or parts. If you're familiar with things like MMPDS, which is an organization that dictates aerospace level material properties, that is starting to gain traction with the additive community, but I can't go out and find a handbook from Timken Steel that says your 4140 steel is going to have the following properties. This doesn't exist in additive yet. We're too young. As you partner with machine OEMs, you should be asking for things like you see on the screen here. Give me all of the data that you have and tell me the pedigree that's behind it. And by pedigree, I mean, can I believe the data that exists? Do you know the powder history? Do I have a heat treat? If I don't understand the back, kind of the first 8 steps, that 9th step of characterizing, pulling a tensile bar, looking at microstructure, there's no reason for me to believe any of that. So when you come to an OEM like GE Additive, we will be able to, should be able to provide you with a data package that you can use to do any future buy-in activities or assessment activities for the new model, new parameter set, new powder vendor, any change you're looking to make. Should be able to provide one of these. So what I've shown up here is a data set we actually generated with the US Department of Defense And you can see on the rightmost column of that table how many specimens are in this data set. It is very rare to see 20 fatigue crack growth specimens available for analysis as you're looking for pedigreed data. But that type of test is the type of test you should be performing to go check for those non-standard measures of buy-in. So a robust data set will include tensile, fatigue, some crack growth if you need it, chemistry, microstructure, pretty much anything you see up there is the intent of these types of data sets for buy-in. Need to have something against which to judge your future process or machine health. So here's an example. This is not real data. I did some Excel engineering just to make a pretty looking plot. But on the left-hand side, what I want to kind of get across is that we should have baseline data. So this is coming from things like that data set that I just showed on the prior slide. This was generated with a pedigree, and I understand where it comes from, and I trust this data. So you're seeing the individual dots in blue showing a 2% yield strength with temperature, and then underneath that, a statistical analysis that we've done for a design minimum. This might be a -3 sigma, it might be a 95-99. There's all sorts of ways to set a minimum design value, but we, in general, are going to take our initial process, get an average for generic design, and then a design minimum, which we should not exceed in any critical application. So baseline data. New data on the left. So because we talked about GE Additive's M-line machine yesterday, we'll use it as an example here. So let's just say I put new material, and that means the same alloy, but another powder lot on this new machine model. I'm going to go through and do a print activity where I'm looking at what the strength of that material is and compare it against the incumbent data. So the question here is then, how do I prove statistical similarity between M2 and M-line? And the better question is, why would I want to? Is because if I can show statistical similarity from new to old, the level of effort that I have on the new machine is much less. I can go back and reuse most of that data, and the new machine model can now be introduced, or new powder vendor, new particle size distribution, anything we're changing can be checked against the incumbent set of data, which I had to have anyway to go through and actually qualify a component. So I'm definitely going to have what's on the left, and hopefully this data on the right, I can show similarity so I don't have to generate that full suite again. So here's some mini tab magic showing the 2.2% yield strength residual between models. If you're unfamiliar with what a residual is, we're taking a line like you see regressed, that dark blue line on the left-hand side, and just calculating how far those points are in vertical space from that line. And then I'm comparing the residuals, so how far they are, across an entire population. Otherwise, I would need to do this on every temperature that I went and tested. So residual is a nice method to consolidate. So what I'm looking at on the left-hand side is the 95% confidence interval for the mean. And when I actually run the ANOVA and get my p-value out of the statistical analysis, we can see, and I don't even know if you can read this, I think it says 0.734, something like that. And at a 95% confidence interval, all I'm looking for is better than 0.05. So we can show for this data set that exists on M2 to M-line that the new data buys in, it is statistically similar to the old data that I had. So in that way, I can say all of my new M-line data on a yield strength basis, I can reuse the M2 data, the prior generation of that machine. The only thing you'll see here, though, is kind of strange, is I've only talked about 0.2% yield strength, and that's not even 1/3 of the results from one test. If I pull a tensile bar, I'm going to get ultimate tensile strength. I'm going to get elongation. I'm going to get UTS. Oh, sorry, I already said that. Yield strength. I'm going to get elastic modulus. All of those things that exist with a tensile test need to go through the same type of activity. Just yield strength on maybe one orientation or whatever the example may be is simply just not enough. So I want to introduce maybe a concept of bucking statistics, ignoring what it has to say to me. So I've taken the plot that was on the left, and I've shown buy-in, my means are the same. And now I've gotten a result that says, uh-oh, my statistical analysis fails. I now have a p-value that's less than required by my confidence interval. What the heck can I do with this data? So a kind of sane engineer looks at this and said, but that data's a whole lot better. Like, okay, fine, let's go with that. So we have to introduce the concept of practical equivalence and equal to or better than equivalence. So this data, on a statistician level, a purely mathematical approach, you have to say, nope, can't accept it. But what I'm showing you is, hey, this new machine is better. It's possible to get results that are better than the old stuff. And should I throw that away and say, no, I'm not interested? No, absolutely not. It makes a whole lot of sense to consider other measures of buying in or showing equivalence to or acceptability of the prior data set. So there's a cartoon on the right-hand side, and the bars are showing essentially the confidence intervals of different kind of populations. It's just a cartoon. It doesn't represent the data on the right. But if you look at what's kind of between the confidence intervals and dotted lines, that's the incumbent process. I was somewhere between negative and positive over there with my mean centered at 0. So that top line, I can show statistical, practical, and equal to or better than equivalence. So that's great. My process is tighter, my mean is a little bit higher just based on looking at the numbers, and that one's very good. As we move to the next one down, statistically it's the same, and equal to or better than, it's the same. That mean is shifted in a good direction, but it's practically not the same. My spread is wider than it used to be, and I now have values outside of those confidence intervals that I had in my old data set. So this checks 2 boxes, but gets that big red X to say, no thank you on that one. The third one down, I've got statistical similarity, practical equivalence, shifty further to the right, and equal to or better than, but it still fails the same process because that tail is hanging out the right-hand side of my prior confidence interval. The one that I want to focus on, and I'll skip the one that's statistically different, but shows on the interval plot that you see on the left-hand side there, which is the one where I don't fail the equal to or better than, but I fail both practical equivalence because it's high, and I fail the statistical equivalence because my means are nowhere near each other. But again, if we take our mathematical statistician hat off, a handful of these are actually just fine. Like there's other ways to go about analyzing data and understanding, whether or not I should go accept. And that's the difference between the academic mathematical approach and the engineering I need to make and sell components in this additive ecosystem. So this is the same form next from yesterday. Well, I'll wrap up with it on the screen, essentially to say we shouldn't be afraid of change in additive. It's new, and we should be expecting a lot of change to be coming in the next few years. There were a couple of speakers yesterday where there was a question about writing standards and specifically the educational approach. How do we possibly teach our students anything about additive when they exit the workforce, come partner with GE as a customer of ours, and we essentially tell them everything they learned last semester was wrong because we've gone leaps and bounds ahead of what the textbook says when it was published a handful of months ago. So we are just moving too quickly to not have a strategy for implementing change. And on a statistical level, the things that we've talked about in the last handful of slides in the last 15 minutes here is to understand where we were, go characterize where we are today, and then figure out what types of overlap that has in order to decrease our burden from generating huge swaths of data every single time a parameter set or machine model or powder OEM or build location is changed. And this is was the best effort that GE has put together on how to handle that change that is natural and almost required by this nascent industry. So that's it. Thank you.
Thank you very much for your excellent presentation. We're going to start our Q&A session. Someone has a question for Daniel? Dr. Alex, please. Mm-hmm.
Daniel, you showed to us that there is a lot of, you are trying to get results that are repeatable. However, I'm just wondering, if the human factor was also considered in that, because it depends on who is running some kind of experimental data, and if different people are there also. How are you taking that into consideration, the human factor?
Yeah, in fact, not only just human factor, but also planned and institutional factors as well. So when performing any type of buy-in activity or characterization to begin with, we are going to go through and introduce intentional variation. So that means building our data sets from multiple serial numbers of machines, multiple powder lots, if possible, multiple powder vendors, actually changing the source of that material. We will then take the specimens we get off of a single build and then divide them among multiple heat treat options. So they're getting the same heat treat cycle, but one half of the build platform is doing that cycle on Tuesday, and one half of that cycle is doing it on Wednesday. So we are intentionally seeding variation into that data set, because if we got all of our data from one build, one serial number, one powder lot, one heat treat cycle, one operator, there's not enough variation there to represent what those parts are doing under production. And we can't believe a data set that's too narrow. So like I said, we're intentionally seeding that with both human factors and kind of institutional, actual sequential stepwise changes in the process.
Thank you.
Another question. How a Tec de Monterrey, for example, can help you to build up buy-in type of use of this technology? Because we believe we can do a lot of experimentation, we can build up data, we can really demonstrate where to use, where not to use, and so on. So yeah, that will be interesting, something to work with you.
Well, some of our biggest successes in expanding the window of how you can use a machine come from academic partners like yourselves. There was a presentation earlier today talking about pushing the process window around if I have too much energy density, too little energy density, and going and checking that against the data that we had. So in GE, we call those handcuffs. And so you have an upper handcuff and a lower handcuff, where one is a decreased spot size and higher power, which is high chance for keyholing style defects in metal additive. And one we have diffused beam and low power, which is a measure of, could create, lack of fusion style defects. So if we can take that parameter set and try those edges and really push those out, it helps us and our customers in turn accept variations to the process that they may not have planned for. So a log file comes back and said, hey, your laser power was lower than you thought it might have been, or the spot size was running low for the entire build. Maybe that's all right, but we need to build the data to go say that that's okay. So those types of intentional variation of process window are things that I think are valuable to include in a university type engagement, because you can really try the edges of the window.
Yeah, but some of the things that we were discussing also is that we have to really have the equipment installed in the conditions that usually you're working in the industry.
Sure.
So probably also to control the environment, because I think variations will really make the machine work differently, humidity, temperature, yep, air conditions, gases, and so on.
And when it comes to I don't want to call them intangibles, because you can feel and you can test and you can control them, but those types of things like environmental control in your factory, our customers are all over the globe. So some of them have very tight humidity controls and some do not. And we don't make any effort in our data collection to go down some of those super niche and super specific investigations. So do I want you to control the atmosphere of the pit facility? Not necessarily. Would we benefit if you wrote down what it was on the day we printed those bars? Yeah, because then that can be fed into the pedigree models that we have and say, does humidity seem to increase porosity because you have agglomeration of powder particles because of the moisture? So it's that type of maybe unintentional variation, but can still be captured in pedigree, that would be helpful to kind of bolster our data sets and the data sets of the broader additive community.
Thank you very much. Thank you very much, Daniel, for your presentation.
Thanks.